So this is lecture 9 on group theory. We're starting with the definition of the group, which I discussed on Monday and it's very explicitly done in the very first page of chapter 2 in the textbook. So a group is a set that has with some multiplication of elements, some binary operation, which is associative, for which there's an identity element, and every element has an inverse. And we don't assume that the multiplication is commutative, but we say that G is an abelian group, or equivalently a commutative group, if AB equals BA for all elements A and B in the group. And we'll see some groups are abelian and some groups are not. Okay. So what are some examples of abelian groups? We have, for example, let's say Q star, which means the rational number is Q, right? Q equals the rational numbers, that's our standard notation. So this is the rational numbers with 0 removed. So this is the non-zero rationals with the binary operation of multiplication. And we know that AB times C is A times BC for all A, B, and C that are rationals, not 0. And 1 times A and A times 1 are equal to A. So the identity is the number 1. And A inverse is just the fraction 1 over A, right? So if you take, for example, 2/7, the inverse is 7/2. And this is true because 1 over A times A, or A times 1 over A, they're both equal to 1. And of course, it's abelian because AB equals BA for rational numbers. So this is an example of an abelian group where the binary operation is multiplication. Another example is Z, which is the integers under addition. But you know that A plus B plus C is A plus B plus C for all integers A, B, and C. 0 plus A and A plus 0 are both equal to A, so the identity is 0. And the inverse of A is minus A. And you have 7 plus minus 7 is the identity. And of course, A plus B equals B plus A for all integers. So the integers form a nice example of an abelian group. These are both infinite groups because they're infinitely many rationals and infinitely many integers. What about a finite abelian group? If you take ZM or Z mod MZ, your choice of notation, which is the congruence classes modulo M. So fix an integer M, that's positive. So these are the classes A plus MZ, and you can choose representative 0, 1, 2, up to M minus 1. And we know that if you define addition of congruence classes, as follows, so this is addition of congruence classes. We already saw several times that this addition is associative. The congruence class of 0 is the identity under addition, and the inverse of A plus MZ is minus A plus MZ. So this is a finite Abelian group. It has exactly a number. Any questions about this? So a group that's not abelian is called a non-abelian group. So simplest example, not a simplest example, but one of the most important examples of a non-abelian group is 2 by 2 matrices with integer coefficients. A, B, C, D are integers. And the number AD minus BC, which is called the determinant of the matrix, is equal to 1. So for various reasons, this group is called SL subscript 2Z. So the 2 means the 2 by 2 matrices, Z means the coordinates A, B, C, D are integers. SL stands for special linear. That's just another way people sometimes say that AD minus BC equals 1. And the operation is, the binary operation is matrix multiplication. So if you don't know how to multiply 2 by 2 matrices, I will tell you right now, ABCD times EFGH. So you take first row in this first column, that's AE plus BG. First row into second column, AF plus BH. Second row into first column, CE plus BG. Second row into second column, CF plus BH. So this is the definition of matrix multiplication. You have 2 matrices, this is the product. So for example, if I took 1, 2, 3, 4 times 5, 6, 7, 8, I would get what? Well, 5 plus 14, 19. 6 plus 16 is 22. 15 plus 28 is 43. 18 plus 32 is 50. Actually, this is the definition of matrix multiplication, but these matrices don't have determinant 1. So this is matrix multiplication. Let's look at an example when we're multiplying 2 matrices that are in this group. I'm playing it in the group. So suppose I take 3, 2, 4, 3. So for this matrix, 3 times 3 minus 2 times 4 is 9 minus 8 or 1. So this matrix satisfies my conditions. It's a 2 by 2 matrix with integer coefficients. And what about minus 1, 3, 5 minus 2. Here I get minus 5 plus 6 is also 1. Minus 5 plus 6 is 1. So both of these matrices have determinant 1. When I multiply them, I get minus 3 minus 4 is minus 7. 9 plus 10 is 19. Minus 4 minus 6 is minus 10. 12 plus 15 is 27. So that's the product. And what is the determinant? So it's minus 7 times 27 minus 19 times minus 10. Let's see. 7 times 27, 7 sevens are 49. 7 twos are 14 and 4 is, that's minus 189. Plus 190. 190 minus 189 is 1. So that's example. So here I have two matrices of determinant 1, and the product is this matrix of determinant. And it's a long calculation, which I'm not going to go through right now, to show that matrix multiplication is associative. What is the identity? The identity matrix I is 1, 0, 0, 1. And if you take any matrix A, B, C, D times 1, 0, 0, 1, you get A, B, C, D. And in the other order as well, this is the identity. The inverse is a little bit tricky. If AD minus BC is equal to 1, and if I have the matrix A, B, C, D, the inverse is going to be, I think, D minus B minus CA. Why would that be true? So suppose I take A, B, C, D times D minus B minus CA. I get AD minus BC minus AB plus AB, CD minus CD, minus BC plus AB, or AB minus BC. These two are just 0, and this is 1. So this matrix times this matrix is the identity. And you can check when you multiply in the opposite order. It's also correct. Let's do one more calculation. I multiply these two matrices together and I got this. Suppose I multiply them in the opposite order. Suppose I go minus 1, 3, minus 2, 5, times 3, 2, 4, 3. What do I get? I get minus 3 plus 12 is 9. Minus 2 plus 9 is 7. Minus 6 plus 20 is 14. Minus 4 plus 15 is 11. And which, by the way, you can check the determinant. 9 times 11 minus 7 times 14 is 99 minus 98 is 1. But the important thing is I multiplied the matrices in one order, this times this, and I got a matrix product. In the opposite order, I get a matrix product, but they're different. So AB is not equal to BA for all matrices A and B in this group. So SL2Z is a non-abelian group. It's not all groups are good. Any questions about this? If you haven't seen matrix multiplication before, at least for 2 by 2 matrices, I just gave the definition, and you cannot leave an algebra class without knowing how to multiply matrices, certainly 2 by 2 matrices. So you need to invest some time in improving your matrix multiplication skills. Let's look at another example of a group. This is sometimes called the affine group. And this is going to be the set of all functions, or ordinary functions, where f of x is ax plus b for some non-zero a in any b. It's just all linear functions, right? If you look at f of x equal ax plus b, it's just a line with y-intercept a, y-intercept b, and slope a. And let's look at composition of functions. As our binary operation. So suppose f of x is ax plus b, and g of x is cx plus d, where a and c are non-zero. So what is f composed with g of x? That means f of g of x. That means f of cx plus d. When you plug cx plus d in for x and f, you get a times cx plus d plus b. This is acx plus ad plus b. So this is again another straight line. This is another linear function. So let me write that example down again. So if we have f of x equals ax plus b, and g of x equals cx plus d, then f composed with g of x, I just calculated that, that's acx plus ad plus b. And in calculus 1, you learn the composition of functions, any kind of functions, is associative. F composed with G composed with H is always the same as F composed with G composed with H. So this is a particular example of composition of functions. So this is associative. So if we call this group G, or ax plus b, a different from 0, a and b are real numbers. Here's a binary operation that's associative. What is the identity in G? It's the function e of x equal to x. This is equal to 1 times x plus 0, so it's of the form ax plus b, e of x equal to x. And you can check that f composed with e of x is f of x, and e composed with f of x is f of x. So the function e of x equal x or y equal x, that's the identity. And how do you find the inverse? So we know that f composed with g of x is acx plus ad plus b. And suppose we want g to be the inverse of f. So f composed with g, we want this to be the identity, e of x, which is x. So that happens if and only if AC is equal to 1, which means C is A inverse, and AD plus B is equal to 0. There's no constant term. So D is minus B over A, and A is non-zero, so this is okay. So f inverse of x is 1 over a times x minus b over a. So in this affine group, what is a group? Under composition of functions. And if we take a simple example, suppose we take f of x equals x plus 2, and g of x equals 3x plus 4. By our formula for composition of functions, f composed with g of x is equal to 3x plus ad plus b, 4 plus 2 plus 6. G composed with f of x is ac, 3x, plus ad plus b plus 10. And the constant terms are different. These are not equal. So f composed with g is not g composed with x. So this gives another example of a non-abelian group. So this is a lot to digest. If you're taking Algebra 1, then you likely have not seen groups before. And there's an abstract definition of a group, but the examples are very concrete. Are there any other questions about this? So on Monday, I gave some very beautiful geometrical examples of groups. So one can say that the symmetries of a geometric object form a group. So you might take a line segment. By a symmetry, you mean a function from this line to itself, which preserves the distances. And there really are only two symmetries of the group, of this straight line. One is the identity symmetry, that means don't move it. And the other picks it up and flips it around. So flip. That's a symmetry. You can pick up this line, turn it around, put it right down on itself, but you've interchanged the endpoints. So suppose I call this function f. Of course, what happens if you flip it again? If you pick this up and flip it, 0 is back to 0, and 1 is back to 1. So the composition of a flip with itself is just the identity, which keeps everything fixed. And so the symmetries of a line, you have a group which consists of two objects, E and F, and there's the following multiplication table. E, F, E, F. And just like a multiplication table for numbers, the identity times the identity is the identity. A flip followed by the identity is just a flip, or the identity followed by a flip is a flip. But if you flip twice, you get back to the identity. So this is what we call the multiplication table for the group. Remember, a group is completely defined by how you multiply the elements, the binary operation. And here's the binary operation. So the symmetries of this line form a group with two elements. Any questions about them? What about, so this is for a line segment. What about the symmetries of an equilateral triangle? So that's a beautiful triangle where all the angles are the same and all the sides have the same length. Those I sort of label the vertices 0, 1, and 2. Each angle is 2 pi over 3 radians. Let's say each side has length 1. So what are the symmetries of this equilateral triangle? Well, one thing you can do is rotate it by 2 pi over 3 radians, or what in high school you called 120 degrees. So let me call, so this is the center of the triangle. So let sigma be rotation around the center by 2 pi over 3 radians, or 120 degrees. So when you rotate this, 0 ends up here, 1 ends up here, and 2 ends up here. That's sigma. If I rotate it again, 0 ends up here, 1 ends up here, and 2 ends up here. And if I rotate it a third time, 0 rotates down back here, 1 over to here, and 2 up here. So I'm back where I started. So sigma, sigma, sigma brings me back where I started. So we can look at this group. It's really a very beautiful group to study. So we see from this that sigma cubed is the identity. The identity doesn't change the, use the triangle fix. You can actually describe these symmetries by just saying what it does to the vertices. So let's say this is position 0, position 1, and position 2. And so 0, 1, 2. The identity, let me just write it like this. The identity doesn't change anything. So 0 ends up, stays at 0, 1 ends up at 1, and 2 ends up or stays at 2. So this is sort of the identity. And what does sigma do? Sigma puts 0 in position 1, 1 in position 2, and 2 in position 0. So 0 goes to 1, 1 goes to 2, and 2 goes to 0. What about sigma squared? That's when you follow a sigma with itself. Sigma squared, 0 ended up in position 2. 1 ended up in position 0, and 2 ended up in position 1. So I could describe each of these symmetries by just describing where the vertices of the triangle end up moving to. Okay. Yes. So these are three symmetries of the triangle. But they're not the only symmetries. For example, I could fix the vertex 0 through all the altitude, the perpendicular bisector of the other side, and rotate around this line. So 0 is fixed, but I interchange 1 and 2. Or I get fix the vertex 1 and rotate around the altitude, the line from vertex 1 to the perpendicular to the opposite side. So 1 stays fixed, but 0 and 2 are interchanged. And then the third sort of reflection is, here's my triangle, drop the perpendicular from 2 to the opposite side, rotate around that altitude. So 2 stays fixed, but 0 and 1 are interchanged. So rotating around, reflecting through 0, I could call tau 0. The operation of reflecting through 1, I could call tau 1. And the operation of reflecting through vertex 2, I could call tau 2. And these are all symmetries of the triangle. There are exactly 6 of them. And this is a very, very, very important group that we will look at quite often. And again, this is described in the text, and it's also described in more detail in the notes that I posted on Blackboard and email out. Let me give some more examples of groups, because the more groups you know, the better. There's a group which is called the 4 group, because it has 4 elements in it. E, A, B, and C. And the multiplication table for these 4 elements is as follows. E, A, B, C. E, A, B, C. So first, E is the identity. So E times anything doesn't change it. So EA is A, AE is A, BE is B, and so forth. So we get the first row and the first column on the multiplication table automatically. And this group has the property that if you square any of the elements, you always get the identity. So A times A is E, B times B is E, C times C is E. So down the main diagonal of this 4x4 array, I have the identity. I just have to fill in what these are, and we say that A times B is C, and A times C is B. B times A is C, B times C is A. C times A is B, C times B is A. And it's a long calculation, which I encourage you not to do because it's too complicated. It just takes too much time. It's too hard. There are too many things to check. But this multiplication is associative. Let's just take an example. What is, for example, AB times C? So AB is C So AB times C is C times C, which is C squared, which is the identity. And A times BC, B times C is A, that's A times A or A squared. And that's also the identity. So for these particular elements, this equals this. And what about AB times A? AB times A, AB is C, C times A is B, and A times BA is A times C, which is also B. So this equals this. And there really are 64 different equations you would have to check. But so that's why I'm telling you, definitely do not check everything. But this multiplication is associative, and this is a very nice group. Any questions about this? Okay. In a group, multiplication is a binary operation. So A squared means A times A. We can define A cubed to be A times A squared, which is A times A times A. By associativity, that's A times A times A, which is A squared times A. And in general, by induction, you can define A to the n to be A times A to the n minus 1. This just means taking an element A in the group, and you can raise it to a power. This is for n a positive integer. For n negative integer, we define A to the n, A to the n. Let me just write it, A minus n. So this is negative integer. A to the minus n, we define to be A inverse to the n. And A to the power 0 is the identity. And exponents work in a group just the way they do for ordinary numbers. A to the n plus n is A to the n times A to the n. And you can prove this by induction for all positive integers n. Any questions about this? All right. So let's prove some elementary theorems about groups. So let A, B be elements of a group. The first statement says that inverses are unique. What that means that is if AB equals the identity, then B is the element A inverse that is part of the definition of a group. So why is this? We know that There's an element A inverse such that A inverse, and A inverse times A is the identity. So A inverse, which is A inverse times the identity, because the identity times anything doesn't change to anything. But E is AB. This is A inverse times AB. And by associativity, this is A inverse A times B. And A inverse A is the identity times B, which is B. So A inverse equals B. So if B is a right inverse of A, B has to be A inverse. That's the first property. Second property says the inverse of an element is just the element itself. And what's the proof of this statement? Well, we know that A inverse times A inverse inverse equals A inverse. And we know that A inverse, let me do this in the opposite order. A inverse inverse times A inverse is the identity. But also A times A inverse is the identity. No. This is correct. This means, let me just do it the way I started it. A inverse times A inverse inverse is the identity. And A inverse times A is the identity. And by what I just proved, the first part is, that means that A inverse inverse equals A. This element has a unique right inverse. So if you have an element in the group, you take the inverse and you take the inverse of that, you get the identity. And the third statement is that the inverse of AB is the product of the inverses in the opposite order. And the proof is as follows. If I take AB times B inverse A inverse, it's the same as A times BB inverse A inverse by associativity. But BB inverse is the identity. This is A inverse, which is the identity. Which means the inverse of AB is B inverse A inverse.
Professor, do you mind just leaving that right there for half a second?
Sure.
Thanks.
So this you'll find also exactly at the bottom of page 20 in the textbook is proposition 28.
Great, thank you.
Mm-hmm. Now, in algebra, we're interested in sort of what you might call the pure algebraic structure of the group. And you can have two groups which look different, but they're really exactly the same. And the word for exactly the same in algebra is isomorphic. So we say a group G is isomorphic to a group G prime. Isomorphic, what does that mean? Morphic comes from a Greek word that means structure, and iso means equal or the same. So these two groups have the same structure, are isomorphic, if there exists a one-to-one correspondence phi from G to G prime, such that phi of the product of two elements in G is the product of their images in G prime. It's phi of A times phi of B. Such a map phi is called an isomorphism. So to give a very simple example of this, we had the group, I'll call it D2, which is the symmetries of this line segment from 0 to 1. And this group consisted of the identity E and the flip. We just flip this around, E and F. And the multiplication table was E, F, E, F, E, F, F, E. That was one group. We also have the additive group of congruence classes mod 2. 0 plus 2z and 1 plus 2z. This is the set of even integers. This is the set of odd integers with the operation of addition. And the addition table for this group, I just write 0 and 1 for 0 plus 2z and 1 plus 2z. Even plus even is even plus odd is odd plus even is odd plus odd is even. And if I define a function phi from D2 to Z2 by phi of E is the congruence class Z plus 2Z, and phi of F is the set of odd numbers 1 plus 2Z. This is an isomorphism. It sends the identity to the identity, and let me give you another example of a theorem in group theory. That G be a group if the square of every element is the identity, if x squared equal to E for all x in G, then G is abelian. So what does it mean to say abelian? I must show that AB equals BA for all elements A and B in the group. So recall that the inverse of an element is unique. In a group, every element has a unique inverse. And also, x squared equals E means x times x equals E. That means x inverse is just equal to x. The inverse is what you multiply x by to get the identity, and x times x is the identity, so x inverse equals x for all x in the group. So what can we say? If we take AB and multiply by BA, by associativity, this is A, BB times A. That's A, B squared A. B squared is the identity, AEA, which is A times A, which is A squared is the identity. So AB times BA is the identity. So AB, which we know is AB inverse, because every element is its own inverse. So this says the inverse of AB is BA. So AB equals BA. And that's the proof. Because the inverse of an element is unique. Any questions about this? Okay. Let me just discuss one more example of a group, another very important example, and that is called the Symmetric group or the permutation group on n letters. So the book writes this as n sub n, but I usually write it as s sub n for symmetric group. This is the more standard notation. This is a set of all one-to-one correspondences from the set of the first n positive integers to itself. You have a function sigma from the set 1 to n to 1 to up to n, which is 1 to 1 and onto. One way to describe this is as follows. So I can write sort of a 2 by n matrix, 1, 2, 3, 4, up to n. That's the first row. And in the second row, say 1 goes to sigma of 1, 2 goes to sigma of 2, 3 goes to sigma of 3, 4 goes to sigma of 4, and so forth, n goes to sigma of n. And because this function sigma is 1 to 1 and onto, this is just a rearrangement or permutations of the numbers from 1 to n. For example, if sigma is, if n is equal to 3, sigma can be the permutation from the function that sends 1 to 2 2 to 3, 3 to 1. Again, this means sigma of 1 is 2, sigma of 2 is 3, sigma of 3 is 1. And sigma inverse reverses the action of sigma. So sigma inverse of 1, if 3 gets sent to 1, the inverse sends 1 back to 3. If sigma sends 1 to 2, the inverse sends 2 back to 1. If sigma sends 2 to 3, the inverse sends 3 back to 2. So using this notation, sigma inverse of 1 is 3, of 2 is 1, and of 3 is 2. And for n greater than or equal to 3, the symmetric group Sn is non-abelian. Also, the cardinality of the symmetric group, the number of permutations of 1 through n, or the number of one-to-one correspondences of 1 to n with itself, is exactly n factorial, which is 1 times 2 times 3, the product of all the numbers up there. So when n is even a small number like 6, 7, or 8, the symmetric group is huge. It's a very, very, very big group. We're going to spend a lot of time studying the permutation group later. It's important to see it as soon as possible. In fact, it's a nice exercise, not an easy exercise, but a useful. To show the following, suppose we let D3 be the set of symmetries of the equilateral triangle. Let's say this time I label the vertices 1, 2, and 3. And S3 is the set of permutations of the set of integers 1, 2, and 3. Then these two groups are isomorphic. And this is the symbol for isomorphism. Okay, last example of a group for today. Suppose I let Z mod MZ. This is the set of congruence classes mod M. But Z mod MZ star This is going to be the set of all congruence classes A plus MZ, where A and M are relatively prime. That is the greatest common divisor. This is the GCD, the greatest common divisor of A and M is 1. So we know that, I mean, this is the definition of the Euler phi function. The number of congruence classes in Z mod MZ that are relatively prime to M is exactly the Euler phi function phi of M. And Z mod MZ star, this is a multiplicative Abelian group. A very important example. Okay, so the lesson of the week, Monday and today, is to learn to study the definition of the group and to work through all these different examples so you see these many different things which they don't have the same superficial appearance, but they all satisfy the axioms of the group. The integers, the rational numbers, real and complex numbers under addition, non-zero numbers under multiplication, congruence classes mod M that are relatively prime to M, permutations of finite set of integers, symmetries of some geometrical body, 2 by 2 matrices. There are lots of different things. What they have in common is they're groups. And the more examples of a group you have at your fingertips, the better you will understand algebra and do well. Okay, sometime very soon, we should have the first exam. So I need to tell you the date of it. And because there is so much to absorb, I will say that maybe the first exam should be in almost 2 weeks, on Monday, March 4th. So algebra midterm 1, not March 4th, on Monday, March 14th. Any questions about anything? Again, I have office hours almost every day. So I really encourage you to log on to an office hour and ask questions. The best way to understand what's going on. Okay. Then, if there's nothing else, we will retire for the day. It's supposed to be a beautiful day, so try to get a chance to enjoy it. Bye all.